functions. Okay, so today, here we go, is we're going to get to starting to look at what are called inverse trig functions, and I think we need to do a little review on what the inverses mean, first of all, before we get to before we actually get to doing it with the trig functions. So the way we're going to start today is I'm going to pick up what we left off in the last session, where we actually did a scatter diagram and we generated a sinusoidal regression model and did that pretty quickly at the end of class. So I want to pick up with that and talk a little more about that, and then one or two other items regarding modeling practice, because a lot of you are having trouble sketching, particularly if there's been some stretching or squeezing of the functions. Okay, so I want to spend a few more minutes on that. Then I want to go back to some stuff from college algebra that some of you are weak on and talk about inverse functions and what they are and how we create them and some of the restrictions that apply. And once we have a review of that underway, then we'll do this third segment today where we'll actually apply those the inverse concept for sine, cosine, and tangent. Okay? So let's start. I think what I'll do is I'm going to start with a tangent function. Start with a tangent function, and then I'm going to come back to that data modeling problem that we ended the last session with. So let's start with something like this. We all know what tan x looks like, or we should, as a graph. And also always have in your mind what's going on with your unit circle concept, because that helps you make connections to the graph. So we know that if this angle here becomes pi over 2, that the tangent of pi over 2 is what? What's the tangent of pi over 2? Yeah, it's 1 over 0, which is undefined, right? It blows up on you. Similarly, if you had a terminal angle down here, here's your first one, pi over 2. So if that whole angle in there becomes pi over 2, you know this thing's undefined. If you get to 3 pi over 2, where the terminal side sits down here, coterminal with 3 pi over 2, right? Or any 2 pi additions or subtractions from that, multiples of 2 pi, then the tangent of that, likewise, is going to be what? Negative 1 over 0 off that unit circle, which is undefined. That then leads you to understanding that if you're at pi over 2 or minus pi over 2, which would correspond to 3 pi over 2, coterminal with 3 pi over 2. I hope you're with me on that. Then we're going to have vertical asymptotes there. And we always label those somewhere off to the side on your graph, so you know where they're located. That should be comfortable. Then we've already earlier in the course talked about what the tangent graph looks like between those asymptotes, and it looks like this. So that's the fundamental character. There's another important piece of this, is if you go halfway between this 0 and that asymptote, you'd be at pi over 4. Pi over 4, you know, is right there on your unit circle. And the slope of that, or the tangent of pi over 4, is clearly 1, isn't it? Or square root of 2 over 2 divided for the y reading, divided by the x reading. If you want to take the long way about getting there, you get 1. So the important points to keep track of are this 0 here, and right here at halfway between that 0 and that asymptote is going to be a value of 1. Okay. It's a fundamental graph. This is as important as you knowing what a parabola x squared looks like and key points that thing goes through back earlier in algebra. Okay. So now let's take a quick peek at y equals the tangent of pi x. And let's say the question, maybe out of a textbook or on a quiz or something, is what's the domain? What's the domain? Or where are the vertical asymptotes? Where are the vertical asymptotes? Like this, okay? Except the problem is here, the angle is now pi times x. Pi times x. Okay? There's several ways of presenting this or answering this question. Here's the ways that we've studied already. If I would put that thing in what I call transform form, I want to write this x and take that multiplier and move it down underneath. And it goes down underneath as the what? Doesn't go down as pi. It goes down as the reciprocal of pi, which is 1 over pi. Good. And I was just helping, I think, Brooke earlier with this, right? And this thing, this number right here is about 1/3, isn't it? Roughly 1/3, 1 over pi. Okay, so what that does is it's going to grab the x, it's going to grab the graph, and it's going to make it roughly that multiplier as wide. All the x readings are going to be made as all the old x readings over here are going to be made roughly 1 over pi, actually exactly 1 over pi times as much as they were. So the multiplying factor is roughly 1/3 there. If you don't like that explanation, then here's another explanation. You know that if we call this, I like to do, I've done this before, if I call that thing the old original, and this is the new thing, then this old x right here is equal to pi times the new x. The new x, then, you can see, is going to be 1 over pi times the old x readings. Roughly 1/3 of the old x readings. Okay. Then, how do you find the period of this particular function? We're dealing with a tangent this time, folks. We're not dealing with a sine, cosine, or their reciprocals. Okay, so we're dealing with a tangent. Normally a tangent's period is pi. You can see it right here off of this picture that you have emblazoned into your brain. This picture's in your brain. The period is pi. It starts a new cycle then after that, doesn't it? Does that thing? Keeps on going. And similarly over here. Okay? One cycle, another cycle, etc. So the period is pi. So that when you're dealing with a tangent or a cotangent, you're going to use a period of pi on the fundamental. But what's happened to that in this new thing? It is made as 1 over pi times this period. That's why I like to put it in this format. And it doesn't matter if you're in a trig class or an algebra class or a calculus course or anything, these linear transforms apply to any function f of x. So if you understand this, it's going to really help you in other areas of applied math. And so then you can see clearly multiplying pi times 1 over pi, the period here is 1. So then, finally, to make a long story short, well actually long story long, is you now have a period of pi, so what you're going to have now is a period that is, a period of 1. The period is 1, which means the asymptotes are going to be placed at negative 1/2 for x and 1/2 for x. And you're going to still draw a tangent graph between those side walls, if you want to think of them as side walls. So you're going to draw a graph that looks like this. And then between the 0 and the asymptote, A half of a half is a quarter. So what's the reading going to be when you're at a quarter?
Pi over 4.
No. What's the tangent of pi times x going to be when you're at a quarter? It should be 1. It should be 1. Let's check it. F of 1/4. Go ahead and do it. F of 1/4. We're going to have tangent of pi times 1/4. And what's the tangent of pi over 4? That's 1, isn't it? That spot checks the sketch. Spot checks the sketch to see if we're on the right track. So, answering the question, where are the vertical asymptotes? Where are the vertical asymptotes? And here's the way the textbook happens to lay this out. They like to use set notation. Hopefully you saw that back in algebra. It's the set of all x such that, math is shorthand, isn't it? A bunch of symbols, but you translate those symbols into vocabulary. The set of all x such that x is not equal to 1/2, right? X can't be 1/2, can it? The set of all x such that x is not equal to 1/2, and then how often do they occur? Every one, right? Every one added or subtracted to a half, right? Plus k times 1, where k is understood to be an integer. You're going to see us use this kind of notation here, this kind of a thing right here, more later in the course. So I wanted to make sure I went over that with you, and then we close that. So then this means, what the examples of this is x can't be equal to 1/2, or if you put a 1 in here, that becomes 3/2. Or if you put a -1 in there, it becomes -1/2. See how it lands right on these asymptote locations? Okay. So that's a little quick review of how you handle transforms of a tangent. Could be a cotangent or any of the other reciprocal functions. Okay, let's find out first if there's any confusion. Total confusion or partial confusion? Any total confusion? No? Okay. Okay, so anyway, practice this a little bit. And then how about the domain? I would probably specify the domain like this. Okay. And so this is actually a nice set notation form for the domain. 1/2 not equal, x not equal to 1/2 plus k. Okay. And then where are the vertical asymptotes? And then you could list a few of them. X equals 1/2, 3/2, -1/2. If you list a few of them, you kind of know what you're doing. Okay? All right. Let's go. Question.
So because there's the vertical asymptotes, does that mean the range is -∞ to infinity?
Perfect. Thank you. Look at your graph here. You can see how low does it start, -∞, and there's no problem rising, is there? All the way up through, there's no breaks in it, is there? So all the way from -∞ to infinity. And the way you want to, and when it says, when it asks you to use interval notation, which is what you're using from this level math on, is for your range, you want to specify interval notation from -∞ to infinity on this particular function. Okay. I'm going to hold off on talking about the secant or cosecant. I've mentioned them briefly. All they do is take a ride. Don't they go for a ride? The secant rides on what? Cosine. Cosine. So when I'm doing a secant function that's got some transformations in it, I draw the cosines picture lightly. with the transforms. And then once I've got that, then I just lay the secant on it, let it go for a ride. Okay, it's not too hard once you get it, but it's really a struggle until you reach that point. Similarly with cosecant. Draw the sines transformed graph, and then let this cosecant ride on that. Okay, let's go back now to where we left off in the last session, which was where we took a scatter diagram of average monthly temperatures for a particular location in the country. And let me show you where we left off. This was, let me get the setup here so you can see it. Okay, there it is. So here's where we left off the other day. And we ran a sine regression model. And it was based on, remember, this list of data. So I'm going to stat, edit. Here is a set of data. And I believe we had 12 data points. 12 data points. Okay, and if you need to, you can go back and watch that video session. And then what we did is we took that and we generated this scatter diagram right here. You can see that that appears to be sinusoidal in its behavior. We then built that regression model by doing this calculation using list of the data set. And you could jot those numbers down for A, B, C, D, and then you'd have the equation of the model. What we then did is we then went here and we stuffed that model into the calculator, into y equals, and it then overlays this model on the scatter diagram. And you can see it working right here. If I pause it, I just hit enter to pause. I can now continue and pause and continue. And the reason this is useful is, let's say this is 2 months, February, right? 2 months later, 2, 4, 6, 8, 10, 12. If I wanted to make a prediction, maybe in month 13, all I have to do is turn trace on. And notice this is now on the scatter diagram, so I can only be on the data set then. If I go down arrow, I'm now on the model. I'm in the trace mode. And so now what I can do is I can come down here on the bottom and I can select 13 to make a prediction about the average monthly temperature in month 13, which is actually here outside the data set. So we are going outside the existing data set to extrapolate what we believe to be the probable value in month 13. Okay? If you go between data points in a scatter diagram, do you know what the word we use for that is? Interpolate. We're going between data points. It's called interpolation. We use this a lot in science, in business applications. So if I wanted to go to, say, month 9.5, I'm going between given data points, and I could predict halfway through the 9th month, in other words, about the middle of September, we would predict the average temperature roughly to be that day, about 63 degrees. Okay? We use this a lot. Now, I want to go back to the data set, and I'd like you folks to read off the numbers that you might have in your notes. So I want to show you something new. So what I'm seeing is 31.8, 34.8, 44.1, 53.4, 63.4, 72.5, summertime, June, 72.5, okay, let's keep going, 77, getting hot, Average temperature, that's pretty high for an average temperature. Okay, how about 8?
75.6.
Oh, coming down. 9,
68.5.
10,
56.5.
11,
46.8.
12.
36.7.
Okay. If we do sinusoidal modeling, build a sinusoidal model of the form A sine omega t minus phi plus, I'm going to go ahead and use k. There's your general sinusoidal model. Now, what I want to show you is how to build this model without having to rely on that fancy calculator. If you can do this, you'll probably be able to get a job in science. Okay, or be able to do something pretty practical if you ever see sinusoidal data collection. Okay, so here's a data set. So amplitude, you know, is how high the thing can go and how low it goes, off the distance off of the axis, right? Off of the axis. So you look in your data set for the high temperature.
77.
Here's our high temperature. Where's our low temperature?
31.8.
Right here. So we have a T low and a T high. So if I am going to then be generating, and I want to leave enough space here to be able to generate this graph over time through a year, then on my first data point, I can see a 31.8, and my high temperature is occurring in month 7. And it's up around 77, then that sets the range, doesn't it? Doesn't that set your range? Your high temperature, your low temperature, and your temperature cycle between those. Where is the axis for this model? Where is the axis going to be?
In the middle between those two.
Excuse me?
In the middle between those two.
In the middle between those two, which means it's the average of those two. This is this high, that one's that high. How do you find an average?
Add them up and divide them by how many you did.
Add them up and divide by 2.
Yeah.
Average of 2 items, right?
Yeah.
So we take the average. So what we're going to do is we're going to find our axis. We're going to find our axis reading for y by taking the high temperature plus the low temperature and divide that by 2. And if you do that, you have 108.8, 108.8 divided by 2, average, or the average on the axis here is going to be 54.4 degrees. So we're going to lay on our graph paper an axis at 54.4 degrees. The range on our model is from 31.8 degrees up to this 77. 31.8 up to 77. Okay. Now, that's from low to high. If this is sinusoidal modeling, then we need to figure out what the period is for this model, don't we?
12.
So here's your low here. Here's your low. Here's your high. Is that the whole period? The difference between 7 and 1? No. The difference between 7 and 1 is going to be about half of your period, isn't it? Isn't that going to be half of your period? is 6 months, the difference between 7 and 1. And so if you double that, your period is 12. Now that should make sense to you, thinking about average temperatures, average monthly temperatures. So the period is 12. We're dealing with a sinusoidal model, aren't we? So we know that period is, what's a formula for period? What's in your brain? 2 pi divided by omega. 2 pi divided by omega. Well, we just figured out the period is 12. Oh, I'm feeling pretty good about this. So now we could find omega in this model. So omega is going to be equal to 2 pi divided by 12, or pi over 6. There's your omega. Now, let's come on back. Let's answer some other parts of this. We just figured out what our angular frequency is. Our angular frequency is omega, happens to be pi over 6. What kind of units are on that thing? I'm going to show you, talk about something new right now. What are the units associated with this value pi over 6? This is strange. We have omega times t. T is what? What kind of units on time in this problem?
Months.
Months, aren't they?
Yeah.
That's time, isn't it? Those are months. T is months. So many months. Omega times t has to be a what? Physically. Thought of as an angle. Doesn't that have to be an angle? Because you're inside a trig function, aren't you? Doesn't this have to be an angle minus an angle to give you an angle here for the whole thing? That whole thing in there is an angle? Okay, so omega t must be an angle, right? And so if that's going to be, if that whole thing is going to be some angle, then like theta or something, then that means, and time is in months, then omega must be in radians per month. Radians per month. So that when you multiply radians per month times months, you get an angle. You get an angle. This is something that drives people crazy when they take physics, because they didn't learn this very well when they took trig. Okay? You know, the physics instructor will just go, oh, this is radians per day or radians per second times time in seconds or something, and you got an angle here, and then you take the sine of that angle and keep on going. Okay, so I'm showing you where this stuff's coming from. Okay, now, so we're back here building this model. We've got this angular frequency value of pi over 6, happens to be in units of radians per month. And then we also, let's see, so we know that value. What about this A right here?
The amplitude.
How do we find that? Amplitude.
Maybe subtracting those two.
Is it at half of the distance between the high and the low?
Yes.
Right. So if we figured out our axis, where our axis is, one way you could do it is you could just take the difference between the axis value and your high or your low. So if you take the difference between that, your amplitude then is going to be equal to 77 minus 54.4, which looks like it's going to be a 22.6, doesn't it? Degrees. When I do subtraction, I always check myself, because I screw it up frequently, by adding these values in my head, because I'm better at addition than I am subtraction. Do you guys do that too? It's a smart thing. Okay, you catch mistakes frequently. And I re-add these in my mentally, and I'm seeing 76.10, which is 77. Boom, checks. Okay, little tricks of the trade. So we got the A, we got the amplitude, we got the omega. Oh, what about the K? On the tail end over here, look at the picture.
This is how much the vertical shift was.
Right, nice. That's how much the vertical shift is. See, we've got a sinusoid doing its thing here, don't we? We've got a sinusoid doing its thing, and so this thing is going to be shifted up by how much?
31.
Normally the axis is down here where my hand is.
Oh, the axis up to 54.4.
Yeah, you take it, you've lifted this whole thing up. Boy, I would not want to live somewhere where the temperatures, although the skiing might be good, where the temperatures, average temperature was cycled above and below zero. That could be pretty uncomfortable, right? Above zero, below zero, different months of the year. Okay, so this whole average temperature thing is brought up to 54.4 degrees, and it cycles above and below that. So your K, the vertical shift, is 54.4. Making sense? I hope. Elizabeth, yes it is. Okay. Right? So the whole average temperature has been brought up. What if you were down in Florida and you collected this monthly data?
54.4 might be the bottom of the axis.
Yeah, it could well be, except this winter. Got a little colder there. But the average temperature may well be, bottom temp minimum might be around this, right? So what you could do, you can real easily, you can go out online and you can just Google average monthly temperatures in different cities. And it might show you big charts of different cities, and you could lay one sinusoid on top of another sinusoid of data, and you could see clearly, you know, how these things cycle and how it varies between different locations, different parts of the world or in this country. Very interesting, useful stuff. Okay, enough of that. Let's get back to finishing the model. We know A, omega, and K. Still got this crazy thing, phi. Phi is called what? I mentioned it previously. No, phase.
Phase shift.
No.
Close, that's close. Almost like, what's that game you play where you make, huh? It's a phase angle. That's an angle, isn't it? Isn't this an angle? Because here we've got an angle minus an angle. It's called the phase angle. It's not the shift. It relates to the shift, but it's not the phase shift. It's called the phase angle. So how in the world are we going to figure out the phase shift? I went over this earlier with you, previously. Without me reinventing the wheel, you can go back to earlier sessions, is it's phi divided by omega.
Yeah.
Phi over omega. So this phi value then is going to be equal to the phase shift. This implies that phi is going to be equal to the phase shift times the omega, or the omega times the phase shift. Now, if I look at my data set, this is going to be a sinusoid, is it not? And here's half the period shown here. We're doing a sinusoidal modeling. See it? Okay. Can you see what the phase shift is of this picture from this data set? Where's the phase shift on here? Isn't it going to be approximately that to where this thing starts as a sinusoid? Wouldn't that be one way of seeing it? See it? So what I'm interested in is seeing what month am I going to choose here? What month will I choose where this thing is about at 54.4 degrees?
Fourth month.
And I look back at the data set, I might guess, right? Doesn't it look like the phase shift is going to be right here just past this spot?
Yeah.
Looking at this data set? And I don't want to necessarily use this next one over here. Okay, I don't necessarily want to use that one because the sine wave is descending there. I'm trying to come up with a sine model that is in our traditional form where it rises and then falls. Right? You with me on the idea? So I do some rough sketching like this, and I observe what I see in the data set where I expect that to be, and I would expect it to be probably a little bit past 4. By interpolating between these. And wouldn't 54.4 be right just probably a touch past 4? Just guess it. Maybe 4.1 months, 4.2 months. Why don't we guess 4.2? So then if I use 4.2, I come over here, and my phi value then is going to be omega, which I think we said was pi over 6, times the 4.2. If I used 4, if I just used 4 to make life simpler, that'd be 2 pi over 3, wouldn't it?
Yep.
If I just use 4 instead of 4.2, this would be 2 pi over 3 for our phase angle. Okay, now I want to get done with this segment so we can move on. So watch this. I'm going to come down here to y2 on the calculator, and I'm going to punch in this thing. So what's our A? Amplitude?
20.
Excuse me?
22.6.
22.6. Sine, our omega is
Pi over 6.
pi divided by 6 times x minus our phase shift, or excuse me, our phase angle,
2 pi over 3.
2 pi divided by 3, close the parentheses, and then add the vertical shift, which was 50.4. Okay, I'm getting excited. Now what I'm going to do, I'm going to go up here, and I want to turn off my regression curve that we looked at earlier. I'm turning it off so by hitting enter up there on the equals, and now the only thing I'm going to graph is what we just built with the scatter plot. The combo of those two. Ready, set, graph. I'm hoping for the best. Oh, feeling good. Isn't this neat? You can build a sinusoidal model, including all that fancy stuff, if you have a data set that appears to be behaving in a sinusoidal fashion by doing what I just did with you. And you can look then at these values and check this out. 22.6, 22.5. Look at this value right here. I guess I'm going to have to punch pi over 6. Pi over 6 is a touch bigger than a half, isn't it? Look at that value. Touch bigger than a half. This value right here is a little harder. If somebody separately had punched 2 pi over 3, how does that compare with negative 2.606? 2 pi over 3? 2.09, pretty darn close. And then look at this, 54.4 or 54.3, 54.4. Okay, that's how you can build yourself a sinusoidal model in some applied course you might be taking. Okay, let's go ahead and end this segment, and then we'll move on to talking about inverses.